So this presentation, as I said previously, is focused on all things designing your next HDPE project. So we'll talk about installation methods. We're going to talk about the material design itself. There's a reason why this generation and this resin material does what it does and allows us to be able to work with it the way that we do in the field. And that is part of the material designation. And Doug is going to come on to start introducing the next one again here in a minute. We'll talk about design, installation, and then the resources that are available to you. So Dan Landy had talked about a few of those resources that are available to you. We love to talk about polyethylene. I can guarantee that everyone on our team today loves to talk about polyethylene, and Richard Colossus' case may not stop talking about polyethylene if you start him, which is a wonderful thing. That's fantastic to have people that are passionate about it. But we do reach across and help with actual calculations, design analysis, and other things of that nature. So Doug, come on over and show us and talk about the material itself. This picture is a very unique picture for us. And Doug, go ahead and take it away.
Yeah, so this picture was actually provided to us by Harvey Svedlik, one of the lions of the polyethylene pipe industry, where he sandwiched together different colored materials and then did a butt fusion. So if you ever wonder how material flows during the butt fusion, this is a good indication of how butt fusion occurs. But we're going to dig into the material first. Alan, if you go to the next slide. So how do we make polyethylene? Well, typically polyethylene is coming from either natural gas or oil-derived sources. In the United States, we're probably 80+% natural gas based. So what comes out of the well is a combination of oil and natural gas. We're looking at that natural gas stream. Now, natural gas is typically methane. What we're interested in is the higher or the heavier molecules that are in that stream, like ethane. So what we do is we fractionate or we separate out ethane in a distillation process. Then we crack that, which means we open up the molecule, get it to bind back to itself to create ethylene. So we basically lose 2 hydrogens in the process. We then take that ethylene gas, we move it into the polymerization, where we start stitching these ethylene molecules together, sort of if you can think of it as like a metal chain. And the more of the segments that we put together, the heavier the material gets, and we go from being a liquid or a gas, depending on the process, into a solid form in our polymerization process. And that's a highly controlled process for us. Coming out of polymerization, we separate out all the reactant materials, so we have just pure polyethylene. That goes into our extrusion process, where we add the necessary additives to get the final formulation. Material gets pelletized. When we talk about pellets, if you think of if you've ever had a Beanie Baby explode, those little pellets, those little BB looking things, that's the material that I make. I then ship that by rail car to the pipe manufacturers and the fitting manufacturers. They load it into their pellet silos, and they will heat that material up and either make pipe or they'll make a particular fitting, as the case may be. So that's kind of the whole thing. We start with the natural gas and we end up with a pipe or a fitting. Next slide.
Hey, Doug.
Yes, sir.
Could you talk to me a little bit? I don't have a lot of data on this, Doug, but I get a lot of questions about the sustainable argument for polyethylene. And, to me, when we used, driving through West Texas, you see all this gas flared off, yet now you're harvesting it. I mean, there's quite a sustainability story there, isn't there?
Yeah, so instead of flaring off the methane, as Peter talks about, and methane is one of the greenhouse gases, we're basically solidifying that methane or the ethane that comes with the methane. So there's a sustainability story in that aspect of it. The other thing you have to keep in mind is that polyethylene, as we're talking about it for pipe applications, is a 100-year plus material. So it's not like a consumable like a milk jug or a carryout bag from a grocery store. These are highly engineered products for long lifetime. So we really don't play into that whole single-use plastic. That's not the area and the type of polyethylene that we use to make the pipe and the fittings. What you see on the screen is an extrusion machine. Up at the upper left-hand corner is the extruder with the hopper. That's where the material comes in solid form. By the time it exits the extruder, it's now molten. So it's a liquid material, but it's a fairly highly viscous material. It goes through a vacuum tank where it's sized, a cooling tank for further cooling. All of that is being moved along by the pulling head. We have a wall monitor so we can understand the wall thickness and the OD of the pipe. And then finally a cutting head where we can cut the pipe into various lengths. 40 and 50 feet are typical for stick pipe. We can also coil material up to 6 inches in diameter onto reels. So those could be continuous lengths between 250 feet and several thousand feet, depending on the OD of the pipe. So that's your extrusion machine for making pipe. So polyethylene and polypropylene are thermoplastic materials, which means we can heat them up. Basically, that gives us the ability to buff fuse the material, and then when we cool it back down, it's still polyethylene or still polypropylene. And so it can be repeatedly heated and cooled. It retains all of its physical properties, as I said. And thermoplastics are materials like polyethylene, PVC, polypropylene, and nylon. In contrast, there is a collection of plastic materials called the thermosets. Now, thermosets, you're going to best know this as an epoxy material. So if you've ever mixed epoxy with a hardener, you get a certain cure time, and then it's basically a solid. You can't do anything with it. So it goes through a curing process, which changes the physical and material properties of polymer, and it's irreversible, as I said. If you want to think of it from a food standpoint, thermoplastics are chocolate, thermosets are eggs. Once you cook an egg, you can't get it back in the shell. Thermoplastics, you can. You can reform the material multiple times. So that's kind of your difference between thermoplastics and thermosets.
So I'd like to jump in here just real quick. So one of the key things from a contractor's perspective for us that's unique about a thermoplastic material is it's repeatedly allowed the contractor to continue to work with this product in the field. If there's a small error, they misjudge some type of a length and it's too long, they can cut it shorter. And it allows for that workability and durability in the field. Another thing that's important to note is any type of fusion process, whether or not it be butt fusion, extrusion, socket fusion, saddle fusion, any of those things, when we control what's happening at a molecular level, all of those are the same. So that fusion process, no matter what, of handling that resin appropriately makes every single one of those processes the same. So that's why it's so durable and workable in the field and really is forgiving for that contractor.
Yeah, so we had a question come in talking about if there's any degradation that occurs in the heating and cooling process. And there will be, but the resins that we supply into this market, the polyethylene material we supply, is highly stabilized. So it's designed to be able to be heated and cooled multiple times and still maintain its physical properties. So we have a very robust stabilization package that helps kind of keep those polymer properties through multiple heat cycles. So that's a good question. Thank you for that.
Doug, could you contrast that? I mean, one of the fantastic things, Doug, about polyethylene is you can repeatedly heat and cool it. So that's why I love that question. I agree with you. But how do you compare that to PVC, where those multiple heatings and coolings are not okay?
Well, the thing about PVC that you look at differently is that PVC's connection system is a bell and spigot system. And so PVC pipes are stabilized as well, and stabilized for the lifetime that they're expected. They just are not stabilized in the same manner to the same extent as polyethylene.
Well, there is fusible PVC though, right?
There is fusible PVC, but again, that's there's a lot of differences in the stabilization packages, Pete, between polyethylene and PVC.
Mm-hmm.
And so I'm going to choose not to comment on PVC stabilization.
Got it. Thank you.
Okay. What we're showing here is butt fusion. So this is that thermoplastic material. So what happens is we go ahead and we heat up the ends of the pipe and we remove the heater plate. And now that material is still molten and it's allowed to itself to form the bead. So that's what you can get with a thermoplastic material like a polypropylene, a polyethylene, or even PVC from a butt fusion standpoint. Next slide. So polyethylene is a semi-crystalline material, which means it has both crystalline and amorphous phases. Now the crystalline regions give you the density of the material. And so I kind of like to show this example. If you think of these white and black layers as the different crystal layers to the material, but you also have these amorphous areas in between. So in my case, these are actually Velcro, but they basically tie the crystal structure together. And so the ratio of that crystalline to amorphous phase really allows us to tailor the properties. So by tuning those, we can tailor our properties for tensile strength, for stiffness, for chemical resistance, and permeability. So polyethylene is a semi-crystalline material, similar to other materials like polypropylene or polyamide nylon materials. Next slide. So what a semi-crystalline material does is it has a rubbery or ductile state, which gives you their toughness, your impact resistance, and also your resistance to rapid crack propagation or fast-moving cracks down the length of a pipe. Semi-crystalline materials also have a very sharp melting point, and that melting point is when that crystal structure basically melts and goes to a fully amorphous material. And it really helps to resist the cracking with a semi-crystalline material. The other aspect that you have, as you see in the first bar chart down in the bottom, is high density actually doesn't become brittle until about negative 130 degrees Fahrenheit. So above negative 130, it is ductile in its performance. When you have amorphous polymers, on the other hand, which don't have that crystalline structure, they are always in a glass-like or brittle state until they get above their glass transition temperature. In the case of PVC, this is 221 degrees Fahrenheit. So in normal installation and use situations, polyethylene is going to be in a ductile form, whereas PVC is going to be in a brittle form. Amorphous materials also, they don't have a very defined soft or melting point, they just soften. And the other issue that you run into is because it's in a non-ductile state in typical use conditions, PVC pipe will behave in a brittle manner. So if you've ever dropped a sledgehammer on a PE pipe, it bounces. If you drop one on PVC, it's likely going to shatter. That's your ductile versus brittle performance and the difference between the semi-crystalline and the amorphous polymers. Next slide. So polyethylene is also a viscoelastic material, which means it responds differently to the load that's applied to it and how long that load is applied. So I like to think of this as silly putty. I'm not going to, when I'm doing this live, I will basically take silly putty and bounce it off the floor. And if you remember playing with silly putty, you throw it against the floor and it acts like a Super Ball. It bounces. So in a short duration load, it behaves differently. But if you allow silly putty to just sit on the counter, for making a ball, what's going to happen. It's going to slowly over time flow like a viscous material. So that's the difference. That's one of the benefits of polyethylene is that depending on the application of the load and the time application of that load, it will behave differently. Alan, you got any?
Yeah, this concept, please take it forward as we move through the presentation, because this one is going to help people out there understand in the open cut scenario why it is that this pipe material still does what it does with allowing workability and durability. So we'll have more graphs later that show the creep and then the stress relaxation of that phenomena that Doug talked about in relation to silly putty. And please recognize the behavior is there, but the strength and durability of that product is also dramatically increased because of the density improvements that we have over something like silly putty. So viscoelastic, take that with you through this presentation, and it'll explain a whole lot of things for you as we move forward.
So when we talk about polyethylene materials for pipe, we have a material designation code. This is a short code. What we talk about as the newest generation of polyethylene is the PE 4710 materials. But there's also a longer cell classification that takes into account 7 different properties of the material. And those are defined in ASTM D3350. Each digit of it, you can see the cell classification PE 445574C. The 4 or the 6 digits, 6 numbers indicate a different material property and a value or range of values for that particular property. Typically, the higher the cell number correlates to a higher material physical property. So in the case of density increases as you go from a 1 to a 2 to a 3 to 4, et cetera. And 4710 materials are typically PE 445574C, and the C indicates black in this case. And then you will also have another position, which is the CC3, which is the highest chlorine resistance, which is not something that we'll talk about that a little bit later on in the design portion of it. So you have a PE 445574C, but we like to call it PE 4710 and make it simple for the non-engineers in the building. Next slide. So polyethylene has evolved over time. It's really an engineered material. It's not an engineered polymer or an engineering polymer, but it has been engineered for specific applications. So the properties that you need for a milk jug are much different than the properties that you need for a polyethylene pipe. They're both polyethylene, but the range, the amount of time a milk jug needs to survive for about 3 weeks, a polyethylene pipe for 100+ years. So we have to design them differently, design different properties into them. And that design has evolved over time. And that's a good thing. If you think about ductile iron, what has ductile iron done to address their problems? They've lined them with cement so they don't corrode on the inside. They've put a polyethylene bag on the outside, or bitumen, or some type of paint on the outside to try to inhibit corrosion. They haven't changed the material. They've just done things to the pipe. What we've done on the polyethylene side is we've changed the material. So we have evolved that material over time from the PE 1404s, which if you've done a home irrigation project, that's that black, very flexible pipe, to the 2408s, which is your medium density type material for gas pipe. That's your yellow pipe, to the 3408s and now the 4710s. We have evolved that material over time to have better pressure resistance, better slow crack growth resistance, and designed out the problems of prior generations. So instead of putting a Band-Aid on it by lining our pipe with concrete, we've designed a better material to make a better pipe. And so that's what we've done over time with 4710. So it's good that our material has changed over time because we've been able to recognize those problems and fix those problems.
All right, we've had a bunch of questions come in, Doug. I'd like to take a break for a moment and answer one of those questions. The question was, is it accurate that HDPE can't be built bigger than 40 inches when slip lining? The answer is no. In fact, Alan's working on a 36-inch slip line up in New England. Alan, are you going DR11 on that one?
DR11, yes. The
Okay.
actual working pressure for the transmission main is 190 PSI. So they need a fairly hardy pipe to be able to put back in there.
Yeah, so DR11 works for you. In fact, I'm working on about 3 48-inch diameter DR11 projects. So that's a 4-inch wall thickness right now. So this idea that we can't do bigger than 40 inches is just not true. We're regularly doing 60 inches and above throughout the US. In the balance of the world, diameters well in excess of 72 inches are not uncommon. It's just in the US, we're not using those for balancing and transmission and getting water from A to B over long distances quite yet. Any color you want to add to that, Doug?
I would just point out that we did a slip lining job in Miami at 56 inches. And that was several thousand feet on a slip lining project. So regularly available is up to probably about 64 inch. Above 64 inch, you're going to have to, the number of people that are producing that, there are less. But we have up to 2 meter, 80 inch pipe available in the US. It's obviously not on the shelf, but it is available.
Thank you.
Sure. So when we talk about polyethylene materials, in the right corner is actually a combination of the natural pellets that I make and black pellets that contain the carbon black master batch. When those are combined together, we get the pipe material. And when we talk about a PE 4710, again, this is kind of the short code version of it. The first digit 4 indicates the material density. The second digit 7 indicates the slow crack growth resistance of the material, which is greater than 500 hours in laboratory test. And then the 10, if you multiply that by 100, that gives you 1000 PSI, which is your hydrostatic design stress at 73 Fahrenheit. And that's the number that plugs into your design equations to determine what the maximum pressure, maximum allowable operating pressure is for a particular system. So PE 4710 really contains all the information that you need. You pop a CC3 on the end of there, and you've got the highest chlorine resistance as well.
Alan, could you give me an understanding of how you take this information that Doug just talked about and you put it in our specs? And does it need to go in our specs? And if it is, what's an inspector supposed to do with this?
So where this is reflected in the Alliance for PE pipe specifications, we reference manufacturers, pipe manufacturers that meet the applicable ASTM standards. So within an ASTM standard, the pipe manufacturers and resin manufacturers have to go through a significant amount of testing in order to be able to stand up to say that, hey, this product, this resin, and this pipe material product actually meets all of this rigorous testing even before it leaves the facility. So this isn't like a field manufactured pipe, like a cured in place pipeline or something of that nature. So the Alliance specifications list those ASTM standards, list qualifications as to which the pipe manufacturers have to meet in order to be able to provide that, and points the user, the end user, the municipal user, that's you, in the direction as to which you can direct the contractor or whoever's providing your pipe with that information. The industry itself, because there are so many tests that are done and put together, go through, again, a rigorous testing material. And here's a good example of the long-term hydrostatic strength test, to where they're proving beyond a shadow of a doubt that they're going to make that long-term hydrostatic stress basis that they're looking at. There's belt and suspenders safety factors already included within this calculation itself, as well as a litany of massive testing that goes into it. So that's how that would happen, Pete. And Doug, feel free to tell us about the hydrostatic.
Yeah, so the question becomes, how do you know that's going to last greater than 100 years? Well, we're not going to wait 100 years to do the testing. We're going to do accelerated testing. And there's been a long proven methodology for doing this, which is the long-term hydrostatic strength testing program. And what we do here is we test at a variety of different stress levels, and those are the little X's that you see on the blue line. And then we fit a regression line to that. We do that testing both at room temperature at 73 Fahrenheit. We also do it at 140 Fahrenheit, and an elevated temperature of whether 182 or 190 Fahrenheit, depending on how you want to perform your testing. And what it allows us to do is we test out to 10,000 hours. And at those elevated temperatures, we can then back that temperature down to 73 Fahrenheit, but we can extend out in time at 73 Fahrenheit. So we can do a time and temperature shift on the material. And what that tells us is that we can go out to 50-year or 100-year projections on what the strength of the material will be. I will say that polyethylene has been used in water pipe applications in Europe since the early 1950s. So there's 70 years or so of data in field in Europe, which has no failures on the material because of a failure in long-term hydrostatic strength. So we know that the material is going to survive for a long period of time through this testing. And there's a lot more detail that we can go into here, but what we do after we set that blue line is we look at the intercept at 10,000 hour or 100,000 hours, and make sure that it's above the 1600 PSI limit for the HDB or the hydrostatic design basis of the material. We then apply a design factor to it. You can think of it as a safety factor. It's not, but it basically reduces that stress down a little bit further down to the 1000 PSI, which is our hydrostatic design stress at room temperature. So that way we're not operating that pipe at its absolute limit. We're providing a little bit of a cushion in there by using the HDS of 1000 PSI in our pressure calculations.
You know, for years, Doug, we talked about HDS and we explained this to our engineer colleagues, and a lot of people's eyes gloss over, and I'm sure some of them are today. And I don't want to diminish this, and I think this is a really important slide to this talk. But I'd really like to add a slide, Alan, after this that talks about the UK Water Research Group's 2020 study when they exhumed 50-year-old first and second generation polyethylene, and that stuff tested new at age 50 years. I really think it's important to bring it to the practical too, because this really makes our case that, at 50 years, the average age of ductile coming out of the ground today is 48 years, according to AWWA. Well, for us, we ought to do our own studies and not rely on the United Kingdom. But hey, Doug, that's profound. That excites me.
Yeah. And as Peter said, all the studies that have been done on exhumed pipe that was installed in the 50s and 60s in Europe shows that it's testing like it's new. So 100 years, yeah, we've got pretty good confidence in 100-year plus service life. So we talked about the temperature operating range. What happens if water freezes in high density pipe? Nothing, just let it thaw. It'll go back to the way that it was. It will still have all of its characteristics. It's not going to shatter. It's not going to burst. Our pressure service temperature is really between -40 Fahrenheit and 140 degrees Fahrenheit. Now, it's going to be hard pressed to find water that's liquid at -40 Fahrenheit, but for other applications like oil and gas, we have been able to work in those areas. And as we said before, glass transition temperature for polyethylene is -130 degrees Fahrenheit. So it's unlikely that you will ever encounter an installation or any type of situation where you're going to be operating polyethylene in a non-ductile state. And it's impact resistant. Will it survive a large backhoe? No. If you really put those teeth into the pipe, it's going to fail. But a scrape, an abrasion, a nudging, no, you're going to be fine with polyethylene. Alan, you have any comments?
No, let's
Okay. Polyethylene is also self-restrained, and we'll talk about this a little bit more in design, but this is a firewater service line at a mine in Arizona, I believe, where they had a mass wasting event where the ground basically gave way underneath that pipe. And you can see the two employees standing there on the right side. That pipe was actually still holding water and delivering water at this particular time. So it can handle it. Now, this is definitely something you want to fix. But the thing about the self-restrained joints is that if you are in a situation with large amount of ground movement, polyethylene will continue delivering, be it over an earthquake fault line, be it across a mass wasting event. You will continue to deliver the fluids that you're looking to deliver because of the self-restrained nature of polyethylene.
The phenomena that makes that happen is very interesting, because the polyethylene can move both in soil displacement, but also in thermal conditions when it's above ground. But the force that's actually required to restrain it is significantly less than other materials. That's why when we go from monolithic systems from point A to point B, it's called self-restraint. And one of the key questions in the survey at the very front was, hey, what about restraining this to other pipe materials? what you're protecting is not the polyethylene pipe when we're restraining it. We're protecting the pullout of the bell and spigot from all of the other material types, the legacy systems. So there's nothing that stops that bell and spigot connection from pulling out, even if polyethylene wasn't there. If you're changing direction of your bell and spigot system moving along, you need to restrain those joints. That's a key thing. So definitely good to see this picture and then how it applies to a normal municipal water and wastewater application. Great point there.
And again, because we're looking at butt fusion or electrofusion for our joints, we are in a leak-free situation. That's the requirement for the M55 design manual for polyethylene pipe. There are 0 leaks allowed. When you initially test the system, you're not allowed any leaks, and you won't have any leaks unless you have, say, a backhoe or third-party damage to the material. So you have a truly leak-free system. Everything that you are delivering from a fresh water standpoint is getting to your customer. You're not going to have root intrusion because you don't have a bell and spigot on a repeated basis. You don't have any concerns about infiltration of water either, or exfiltration of water or wastewater. It's a leak-free system, and that's the way we design it, and that's what we require for the installation of it. And it's through the wonder of the butt fusion joint, as we show. So electrofusion is also a common practice. Electrofusion, there's it's specially designed fittings that heat up. They melt both the fitting and the pipe that it's mating to. They're very useful for branch and saddle connections. They are permanent. They are an economical way to tap into the pipe and to get that service line coming off of the pipe. It's very important to follow all the manufacturing recommended specifications and procedures. It's extremely important to make sure that the pipe is clean, that it's properly prepared by peeling or scraping. Peeling is the preferred method. You want to use qualified operators. Make sure you're getting somebody that's trained. Write a good spec. Make sure to train your inspectors so that they know what to look for. And electrofusion is just as reliable as butt fusion. And we can refer you to the PPI handbook, chapter 9. There's also municipal advisory board recommendations for electrofusion as well. Very useful data out there, very simple data and simple procedures that will help you to make for a proper electrofusion joint. When you're electrofusing, you have a connection to the power source, and you have what's called a hot zone and a cold zone. The hot zone is where the resistance wires are located. The cold zone allows material to flow from the hot zone into the cold zone, creating a much better joint. So if you click the next slide, you'll see your hot zones and then material flowing into the cold zone. So the material actually flow, in this case on this coupler, into the joint between the 2 pipes. So you're basically allowing material to flow, and a little bit will flow outside of the coupler as well. So that gives you a fully formed joint all around the circumference of the pipe in this case, or the 2 pipes in this case with the coupler. Next slide.
We've got a couple of good questions too.
Okay.
Doug, we had one. Are there electrofusion tees for hot tapping into HDPE, or do they still require mechanical connections? So if we're performing service connections to that main line, there's a lot of electrofusion connections available to you that are self-tapping as well. So once you make that connection, you can go through and make that final connection as it goes to a service line directly. Anything that is the full diameter of the pipeline that is put in typical to an inserted tee or something of that nature, which is a encompassing fitting that cuts out a coupon to be able to remove and then puts in the wedge or the valve wedge. They're not there yet on electrofusion fittings, to my knowledge, to date. So any type of a full diameter eclipse from a mainline standpoint, we're not quite hot tapping yet, but very often we use fittings in that nature.
But there are saddle connections that you can use to make your connection to a home or a building. And on the wastewater side, there's also 45-degree elbow fittings that can be used. And those can be hot tapped onto the side of a wastewater main as well. And they can be drilled right in from Faction Fusion. So we do have those available. Again, if you're going to build a T for, say, a fire hydrant, there are electrofusion Ts. There's also butt fusion Ts, but not a T for a hot tap, as Alan's talking about, except in the case of the service connections for water and wastewater.
I want to distinguish the phrase hot tap very specifically, because there are definite size on size connections that can be made, but a hot tap is one of those where we're looking at live water and wastewater flow under pressure through that pipeline. So for gravity sewers, there's a whole lot of options as to which you would temporarily block the sewer through it. In pressurized applications, if you can't shut off valve to valve to isolate that section, to cut into it and drain it, then that insert a T is one of those things that I was discussing, and that's specifically to address the term hot tap.
Right.
So that's, and then we had another question within the chat, whether or not polyethylene can be used for natural gas. Most of the lessons that we learned that we're presenting here are from natural gas, where it's 95% of the pipe material type. And this discussion of hot tap, they do something called a squeeze off on either side, where we would fully eclipse the pipe diameter in order to be able to isolate a line, and then make whatever work you want through there. And it's one of the primary ones that is used for natural gas distribution itself.
Yep.
So electrofusion as well. I said this earlier, and I just wanted to restate it as we go forward. Electrofusion, butt fusion, extrusion, saddle fusion, socket fusion, when we properly handle and process all of the polyethylene at a molecular level, the same thing happens throughout it. So we have ASTM standards, we have MAB guidance for you, we have all of that sort of thing that happens to make it so that the joint that you put into place, or the fitting that you put into place, is as strong, if not stronger, than the actual pipe material to begin with.
Yep.
There's an example of a fitting. So what are we looking at here, Doug, before we move on?
So what you have is a coupler here. So we have a fabricated elbow to the left, butt fuse fabricated elbow, and we've got an MJ adapter ring to the right. And so we're basically coupling between that elbow and that MJ flange adapter ring. The operator here is scanning the barcode with a scanning device. He's already got the leads hooked up, has the power pack there in the right foreground, and then a generator, not a welding generator, but a typical electrical generator is what's needed for doing these electrofusion connections. And he basically scans the barcode, confirms that the information is correct, and then presses the green button there on the yellow power pack.
Yeah, so that's an electrofusion processor. That's an old one. We need to update this slide. But Alan, this operator has chosen to use electrofusion, an large diameter electrofusion coupler, to connect his fabricated fitting to this mechanical joint adapter assembly. Could you tell us all the components of an MJ kit that contractors can purchase at their favorite distributor?
Sure. So an MJ adapter is going to be a belt and suspenders approach to have a restraint joint. So that restrained joint itself can have the stub as to which it's manufactured in the manufacturing facility, that has that stub of HDPE pipe with a lip that subsequently has larger material from a high density polyethylene that's put around it. That lip will have that gasket, that flange that pushes up against it in order to be able to be bolted up to a valve or other connection that you want it to be connected to. And then each one of those bolts, there's a PPI technical note on how to make sure that you torque those bolts appropriately. So it'll show you the tension as to which you have to do it, the manner as to which you have to do it. When that MJ adapter is fully connected to your valve or your fitting or whatever you're connecting it to, it is considered to be a restrained joint. It can be done under wet conditions as well, which any water operators out there, in water main failures, we have a lot of water. So sometimes it's hard to shut all the valves off from your valve actuating program that you should be doing to make sure that those wedges properly seat in whatever pipe material type you're using. But the MJ adapter is one of those belt and suspenders fittings that overcomes any presence of water through this process.
That's a great explanation. Good job. Dan, could you bring on the second and final question? And while we're looking at that question, Alan, I'd like to answer a question live that we're getting from our audience. And that question, Alan, as our audience looks at the poll question is, how does polyethylene compare to ductile iron when constructing in areas with known VOCs? This is a really important thing because many of our guests today, Alan, have to design in bad soils. Take it away.
Okay, so as a civil and environmental engineer, the very first thing I would say to you, if you know that you have an area, a brownfield with one of the BTEC's presence of hydrocarbons in the soil. We know there was a gas station, there's some type of a manufacturing, whatever it was, whatever put the pollution there. Hey, if we know that that area is already bad, let's remediate it. First and foremost, that would be regardless of pipe material type when we put it back. The bell and spigot, the gasket that is there with the bell and spigot also allows permeation through that gasket. The nature of polyethylene as it's designed does allow permeation of that hydrocarbon through that pipeline. The PPI and the theoretical analysis has been done to show us the derating of that pipeline as we move through it, so we can reduce its strength when we know that there's hydrocarbons in an area and we cannot remove that hydrocarbon. We also need to know the amount of fluid velocity as it goes through. So in multiple analysis of this specific situation, the areas to which we have a low level of our distribution system sitting in a hydrocarbon with no water flow for an extended period of time is when that'll hydrocarbon will permeate through and impress upon the flow through there as well. So again, back to the environmental engineer in me, if you already know that there's hydrocarbons, let's remediate that system. Let's remove that hydrocarbon. If you cannot, there's other systems within polyethylene that dual wall that polyethylene. So we have a pipe within a pipe. This happens all over the United States to handle leachate and landfills. High density polyethylene is one of the primary used pipe material types within landfills to be able to transpose and move the leachate, collect it within the settling landfill mass in and of itself. As that mass settles, so does the soil get displaced, and therefore they're taking advantage of the fact that the self-restrained nature of high-density polyethylene as well. So just a reminder, whatever pipe material type you're putting in, if you're putting in a balanced spigot pipe into a known hydrocarbon, you also have to get an improved gasket that can resist that pollution across it as well. So we're going to keep going. How would you best describe your opinion of HDPE pipe? 3 of us, 2% said we are not currently comfortable using a high density polyethylene. Hopefully we can make that different for you. 33% we will use it when it makes sense, horizontal directional drill. Some within our industry said if we're going to use it for the hard stuff, let's consider using it for the easy stuff. So 39% when we accept HDPE as an equal to other commonly accepted pipe materials, we will use it. And then 26% say HDPE has now become our preferred pipe material choice. So Doug, thank you so very much for leading us through that process. The material behaviors and properties are what we really need in order to be able to make the next step in the evolution of how does it behave while it's installed, how are we working with it as a contractor in the field, and what is the long-term understanding of how this material type will work through surge and other things of that nature. So you're looking at pressure rating for the pipe. We are almost at 3 o'clock, so the top of the hour. This is a 90-minute presentation. We have another 30 minutes to go and a fair amount of material to cover for you. The questions are making this better, so keep them coming. We've had lots of good questions that we answered live, and you're typing through as well. So hopefully you're getting some good results from Dan and Pete and Richard in the background. So the pressure rating itself has factors for it. So if we know that there is a hydrocarbon or some type of a factor for relation to operating in higher temperatures, there's a factor for that. It's a temperature compensating factor, and then we also have the other hydrocarbon compensating factor as well. These are all inversely related to DR. So the lower the DR that we have, then the higher the operating pressure that we go through with these pipe material types. That's important to know. It's based on the wall thickness of that pipeline as we go. The lower that DR rating, the higher that wall thickness that we have in total for the operation of itself. I want to talk about surge and then bring back that concept of viscoelastic material type when we have an apparent modulus of elasticity that changes. And that changes based on an instantaneous load or a constant load as we work through it. And so surge pressures themselves, there's various types of surge in a potable water distribution system or force main system that we're looking at operating. The differences are recurring or occasional surge. The design of polyethylene can withstand recurring surge, which happens 50 times a day thereabouts, which is the pump on, pump off scenario of just responding to water demand within our system itself. The occasional surge, high density polyethylene can resist 1.5 times that operating pressure for the entirety of its lifespan for all pumps on, all pumps off, a massive firefighting event, a water main failure. Water main failure is when we have an open orifice to release all this water. Sometimes our system responds to that and just turns all the pumps on as we go through. That is that occasional surge as we go through. High density polyethylene can accommodate larger surges as we go through that pipeline. That's a higher velocity change of the fluid through it, but we provide actually less PSI increase through that flow through. And that has to do with the fact that we don't have as a high a hoop strength as we go. And PVC and ductile may serve to amplify that pressure surge as we move through that pipeline. That temporary behavior of the parent modulus elasticity that changes for us actually can serve to attenuate some of that pressure surge as we move through that pipeline material type. So here's just an example of those modulus of elasticity that you'll see here through. So a lower modulus for us equates to a lower surge pressure as we come along. Here are the pipe material type characteristics for PVC and ductile iron. And PVC, the recurring surge needs to be taken into consideration for that design or pressure class as we see it. In ductile iron, they simply add 100 PSI through that process in looking at pressure surge itself. So while we're a flexible pipe material, the design proponent that's put forth with 1.5 times the recurring surge and 2 times that occasional surge, on the occasional surge allowance gets us up there. We're right up there with that ductile iron to be able to resist that surge as we come through it. This translates to a fatigue along that pipeline. And all the way back to when Doug was telling you about that hydrostatic design stress. While Pete may have been glossing over, and sometimes the rest of us do too on some of those tables as we go through it, the simple fact is when they run that hydrostatic, long-term hydrostatic design basis stress test, they are actuating this pipe in a laboratory condition through its recurring and occasional surge to get the actual point of failure to track it down its linear regression. it has to be done in a lab condition to prove that this pipe material is doing what it should be doing and doing it for you. Anytime they change resin, anytime they change any type of process through there, they have to go back through some of that ASTM design standards and subsequently prove that again as well. So that handles that 15 million cycles without fatigue as we go through, and that measures that pressure change as we move through it as well. So we look at flow design. Of course, high density polyethylene does not corrode, so you're going to maintain that Hazen and Williams coefficient as we move through that. If you're on the call, I apologize if you're eating lunch, and I'm going to point you in the direction of looking at a galvanized galvanized water main. If you've never seen the inside of a small diameter galvanized water main, you probably should look at one. The tuberculation essentially comes through, and what tuberculation is a loss of metallic material that provides an opening behind it in order to be able to lose even more material to where we're getting to these tubercles that basically allow pinhole flow through this. If the American public was to generally see heavily corroded pipelines that they were drinking through, they would probably want immediate change. I'm not even talking about biomass that can live within that tuberculated area without proper disinfection in some places as well. High density polyethylene does not corrode. We do not provide that spot for that biomass to accumulate as we move through it. And that Hazen and Williams coefficient factor of friction loss through this does not change over the lifespan of its pipe. And the lifespan of the pipe material type. It's a very, very good characteristic of this as well. Chlorine resistance, the industry on whole has moved to a CC3, which is a much higher rating of chlorine resistance. But one of the things that I wanted to point out with the equation is the theoretical's there in the Plastic Pipe Institute. They've done this work a long time ago to look at chlorine and how it affects polyethylene, isolated throughout polyethylene. Historically in the 80s, there was a service connection that was both hot and high chlorine as they had it, and small diameter service lines had some failures within the southwest parts of the United States. And then also chlorine dioxide is used in a treatment, so a primary chlorination unit and not a continuation or a secondary chlorination unit throughout the pipelines and at the plant where they're putting in chlorine dioxide. In some places in the United States, they've seen interaction with high density polyethylene as well. We've looked at those in a Water Research Foundation study across average municipalities that volunteered for this study throughout, studied temperature, chlorine, operating pressures, the pipes that they had in place, and everything is achieving above 100 years. So that's that 0.2, which is the minimum limit out in your distribution system, through the 5 milligrams per liter of the EPA limited disinfection that we're fitting through with this pipe material type behaviors. It lasts long and does not degrade in those scenarios and conditions as we see it. We talked about hydrocarbon contamination earlier. Studies have been done to prove hydrocarbon contamination and how polyethylene behaves. That information is available to you within Plastic Pipe Institute's Handbook on Polyethylene Pipe and other studies that they have for you as well. But I'll circle back around as a good environmental engineer. We're going to try to remediate first and dual wall second as we go through. Okay, so we moved through that rather rapidly. Any questions that we need to address, Pete, before we move on to the major installation methods?
No, we only have 2 open and we're working on them. Thank you.
All right. So this section, and we had a question early on about open cut construction and how the pipe behaves. And then I've got cool graphics for you on viscoelastic behavior. So that way you'll see that the flexible pipe material that we install for high density polyethylene interacts with the soil as a pipe soil structure and transmits all of the loading directly to the soil that surrounds it. I'll fast forward to the end and tell you, PVC ductile and high-density polyethylene, when looked at in an open trench condition, are all considered flexible pipe materials, and they transmit the loading the same way. So you'll get some more benefit out of that from just a straight soil analysis as we look at it. Okay, so we've changed the way that we have installed pipe fairly significantly in the past 100 years. Much things have changed in general the way we run our normal lives. So high-density polyethylene has evolved. The involvement has not been just in the resin, it's been how we actually work with the pipe material type. So that's the equipment used to move it, to fuse it, to handle it, the fittings, everything. We do a full presentation on innovation within the high-density polyethylene industry that if you see it on our docket, you probably want to attend that at some point in time. But it's been pretty amazing to see just on the outset of this industry how much has changed in how we install or rehabilitate water mains. Here's just a generic over time. A big key thing to point out here is ductile PVC and high density polyethylene were all invented and brought to market around the same time period. As previously mentioned, natural gas was a primary part as to which the high density polyethylene went after, as well as in the oil patch, and then mining operations where the inside of that pipe actually withstands the massive slurry and all the aggressive things that they contain within that slurry in a mining operation to move it through in a high density polyethylene. So that industry has been focused much more so on that than the municipal water and wastewater market. Out of all three pipe materials, high density polyethylene is one of the lower adopted in traditional open cut. With regard to trenchless installations, we're definitely one of the higher. So one of the questions was in the survey, hey, we use it for HDD. Well, then why don't you use it for all the other things too? Is HDD is one of the more challenging installs you're going to have as you go through that. So here in a direct burial of pipes themselves, again, ductile iron, PVC, and high density are the same. Rigid pipes are going to be a pre-stressed concrete cylinder pipe, vitrified clay pipe, cast iron, or asbestos. When we put that load, whether or not it is a H20 dynamic load or a load from the soil column that's on top of this pipeline as we go through that, the point of the pipe in a flexible pipe scenario is to take all of that pipe, that induced stress, and put it to the outside of the soil that's supporting it. So if we did not have soil, you would see that pipe material type deflecting as we went through. But again, once that's properly embedded and properly compacted, that stabilized passive resistance from the soil is what's going to hold that pipe into place, and the reaction there will make sure that we do not have a deformed pipe. I'll go back straight to when you saw that self-restrained title slide with the two happy humans on the thing and there was no soil. The embedment of that pipe on the opposite sides of it still provided enough resistance from that pipe settling as we moved through it. So that's going to be one of the key things that we're going to continue to watch as we go. In a rigid pipe, the hoop stress of that rigid pipe is considered to be much greater than the soil surrounding it. So as a direct loading here that we go through, the rigid pipe is intended to push and put all of that load that we're putting on top of this pipe down into the soil underneath the pipe as opposed to outside of it. So that's an important characteristic distinction between it. And here again, we're going to go straight into the viscoelastic behavior is what we have. There's two primary components to this, and you'll see a graphic here in a few minutes. A creep is a deformation of the material type itself. So that's when we're looking at the silly putty, that's the silly putty pulling apart as we go through. So if you're going to pull that silly putty apart, that's going to be the stretching of the silly putty as we've got it. Now, a stress relaxation, if we stopped that stressor, that load, now the bottom of that silly putty is subsequently going to settle as we go through this. All right, so that's that stress relaxation as we go through in specific to high density polyethylene material as we're addressing. So I have a nice graphic here for you that shows the stressor line all the way up for elastic material. And then if we were to load this pipe with no soil surrounding it, we obviously would put that induced stress and go through, and that would squash down as that creep would occur. Instead, we have soil that surrounds this pipe, and now we're going to stop that pipe from occluding in that manner. Again, the force that's required to stop the high density polyethylene from deflecting is not anywhere near as great as the other pipe material types, and that's why it allows us to take advantage of that material in a different manner. I'm sorry, advantage of the viscoelastic behaviors while we're doing construction and working with it as we go through. The typical terminology of pipe embedment materials for you here. We've got about 17 minutes left and a fair amount of slides to cover through. So I am going to kind of push through quite a bit of this. So that backfill is what distributes the loading through the soil column as we come down. And when it's properly compacted, it'll lessen the impact of the live load. And I've got some fairly good tables for you as we go through. We like to show this video. It's been put on social media and was attacked in social media because they didn't believe that this could be a good manner of installing the pipeline. One of the big things I'd like to illustrate here is there's nobody in this trench, which is another productivity improvement of high density polyethylene use over getting in this trench and putting in your bell and spigot as we go through. But this meets all of the trench characteristics that I was discussing before. They'll just simply compact the material on top. They have a decent foundation as they go underneath it, and it does meet all those requirements. Yes, Pete?
So this was up in New Jersey, and so we're using native backfill here, Alan, as you know, and people also complained, the haters did, Alan, that you can't do that to the pipe. It's bad for the pipe. It's a bad practice. You know what? I kind of agree. The guy's using a bucket to bang the pipe in into the trench, and you know what? He could, in fact, Alan, damage that pipe. However, he didn't damage the pipe because the inspector inspected it. And this guy is really pretty good at it. Proper procedure, I would say, would put a sling on it, not a chain sling or a wire rope sling, but a polyester sling, and lift it and place it into that trench.
Great. So when we move forward, AWWA's M55 manual has a design window for you that looks at a DR7 through DR21. Minimum depth of cover with an H20 loading is that 3-foot depth of cover. So an H20 loading is a box truck that moves over top of this. Minimum depth without that H20 loading is that 2-foot. So we've got a standard design window for you that is typical as to which you would look for safe installations. I wanted to point you in the direction of what could be atypical, which could send up some red flags for you, and I'll try to do so quickly. The two biggest factors for the design equation are the pipe stiffness factor and the modulus of that soil reaction. So the reason why you had a DR7 through DR21 is that pipe stiffness factor for the 7 is significantly higher than we get into in a 32.5. And that's the ability of that pipe itself to resist point loading just by itself. Now, if we had a DR7 in extreme poor soil conditions, then that DR7 itself will take all the loading on top of it. When we calculate the force using the equations that are in the guidelines for you, any pressurized pipeline, so if you put pressure within any of the pipelines, that pressure is formed, that force trying to keep that pressure inside the pipeline is going to be exponentially larger than what you see outside of the pipeline. That's why they give you a design window. It's only those certain operating scenarios as to which we now need to go through the equations, and I'll try to go through some of them for you. When we look at deflection, So that's, we had a question about ovality of the pipe. And that was a good question. I'm not sure exactly who asked it. I'm still trying to power through a presentation. But if you're not operating the pipeline and we allow the weight of the pipeline to go over time to sink, and by the time we put it back in the soil and compact everything, we should be coming back to oval through it. The second that we pressurize that pipeline, that's when all of that compensation is going to come through as well, and we will have a perfectly oval pipeline or circular pipeline as we relieve that. So that's a good observation. Here on the left, that I've circled is the pipe stiffness factor. So that for a 7.3 DR rated pipe is 1600 PSI. For a 32.5 is 12.5 PSI. And that here's the difference in the working pressure. So I'm going to show you some tables basically of the effect of the live loading and the soil loading on your pipeline. And please believe me, by the time that we pressurize a DR 7.3 at 333 PSI, that is going to be what this pipeline sees as its highest loading that we put on the pipeline. When we get under the DR21 and we get into a 32.5, we're going to look towards an engineered backfill. You're going to do that in cases as to which we're going to be looking towards a non-pressurized pipeline anyway. For a VCP pipe or something of that nature, we're going to put in a pressurized and engineered backfill. So Pete had mentioned native backfill. It is not inappropriate to use native backfill when we're looking at it. We have that soil stiffness factor here at 0.061 times that modulus of soil reaction. Now, the compaction of that material makes a big difference. We're not going to recommend use of a class 5 material, a class 4 material at just 100 PSI in a non-compacted condition. If we compact it to moderate, we're going to have 400 to 1500 PSI for high. When we get into the engineered backfills, any roadway base, we're hoping major roadway base, they're looking at flexible asphalt as it stands, and they want to have a good solid base for it that they've imported to support that flexible asphalt base. Is not likely going to have a class 4 soil, but it's up to you as the responsible design engineer to look at what these are. But as you can see, by the time we start to compact these, we get into 6,000 PSI of moderate compaction for that modulus of soil reaction. So we're jumping that up. In comparison, that's an additive on the denominator. So both the pipe stiffness and that modulus of soil reaction are going to work together to dramatically reduce that loading. So now I want to take a couple of minutes and look at the loading characteristic. So this table shows you an H20 live loading. If we are going to be at 4 feet depth, you're going to see 4.2 PSI of live loading on your pipeline at 4.2 or 4 feet of depth. Now look back here. A class 3 and a class 2 uncompacted backfill can hold that 500 PSI range that we're looking at, in addition to what we have for the pipe stiffness factor. Then, of course, you'll calculate the earth load, which is just the density times the depth as we're going through it. When we get into deeper installations, we're looking at 8 feet of depth. Less than 1 PSI of actual loading from the H20 loading on this pipeline is what it's seeing. So we're dramatically minimizing those loading by having good engineering backfill, or even in the design window that they offer from a 3 to 25 feet for a non-H20 loading or an H20 loading on DR7 all the way through DR21. So these things have already been done for you. It's only those specific situations where we're looking for atypical loading scenarios as to which you'd have to perform them for your pipe. And I'll tell you what, most of the pipe manufacturers will give you a table. You'll work off the table, and seldom do the engineers get involved into the nitty-gritty, but the equations are there. Subsequently, the Alliance PE Pipe has spreadsheets working already set up with this for you that you need. So definitely email myself or Dan Landy as we go through, and we can send you those spreadsheets that you can plug in all the parameters that you want to know here. The trench width, what we're looking at is that 3 to 24 inch size pipe is that OD plus 12 inches as we go through. We're simply making sure that the interface of the trench width with the native uncompacted fill as it's there. We're providing ample room to be able to work with the pipeline as we go through. Embedment requirements, 6 to 8 inch pipeline. So this is the bread and butter sizes for distribution systems of potable water applications. This is smaller diameter for gravity sewer applications, maybe a pipe bursting we're looking at. 3/4 inch max particle size. This is important to note for a constructability purpose. And a lot of times when we excavate a trench, the bottom of the trench, if there's presence of groundwater, or if there's other items in there that make it tough to move around for your employees, your crew that's in there, they're going to dump what's called a 57 stone. They call it 57 stone because that's what passes a certain sieve for it to come through. That particle size is directly related to that 3/4 inch. Okay, so that can actually go through and be filled all around the pipe with no long-term stress riser on this pipe as we go through as well. When we get into larger pipe size, so does that particle size as we move through. This is a couple of videos here for you on an open cut lay-in method. So if you've got a long area that you can take advantage of that fusing a large production run of polyethylene in advance, and you can lay it into the trench, this is a perfect way to be able to do so. Developers that are unfamiliar with high density polyethylene pipe, is if they go through a slash and burn on a piece of land and start to look at this, they may very well be able to start to see some productivity levels as to which they will install this pipe in this manner. Also note that they don't need all of the employees in the trench, as I mentioned before, and we're going to get high productivity levels through it. We don't have a whole lot of time to cover HDD. I believe we may be doing an HDD presentation webinar throughout the remainder of the year, but essentially I'll cover over the basics as we've got another 5-6 minutes max on it here. So there are references available for you to be able to horizontal directional drill. Our audience, thank you so very much for telling us that you were familiar with this method. So I'm only going to show you the references as we move through this process and go through it. But essentially, we're looking at friction forces at point C and point B there while we're getting through that bore path. And then friction forces of pulling that pipeline along the top. From a high density polyethylene standpoint, we want to make sure that we're not overcoming the tensile strength of the high density polyethylene. We're making this pull. ASTM standards are going to be your go-to for calculating the friction forces through it, or the Plastic Pipe Institute Handbook on Polyethylene also has that information for you. Here, that borehole friction, it's when that buoyant high density polyethylene rubs up against that curve through that. It'll create some friction forces as we move around that pipeline. Here we have the information for you. We have the calculator for you. PPI Handbook on the Polyethylene Pipe is also in the Alliance for PE Pipes engineering package for you. That'll provide you this information as well as the specification as we go through. We talked about the pipeline being very ductile, or the most forgiving of the allowable bend radiuses. That's very important for inserting it into holes for pipe bursting or pulling it around areas in very tight constricted quarters. I will recommend that you watch the allowable bend radius when we especially get to a thinner pipe wall, because what you'll see in the bottom is a kinking of a 32.5. Now that viscoelastic behavior of the pipe, the workability of the pipe, and durability of a thermoplastic allowed that contractor to come back in, cut this kinked section out, re-butt fuse it, and then continue with his pull. So that's another true testament to the behavior of the product when we're talking about a thermoplastic that allows you to continuously heat, cool, heat, cool, heat, cool, heat, cool. When they get to the oops, You know, it's not always the best timing, but hey, we can just cut this section out. When in doubt, cut it out and keep going. Slip lining is a common method to be able to pull in. We had some good questions about the largest diameter slip lining available. It is the host pipe and the size of the host pipe that's going to limit what size of pipe you can pull in, more so than the technical limitation of the high density polyethylene as we get to it. And here slip lining can happen very quickly in large productive runs as you're seeing large diameters pipes pulled into place. I believe that's a 54-inch that we're seeing on the right that was pulled in within only a few minutes once they had proper access before and after as we go through that. Compressive fit lining is another type of slip lining that is unique to high density polyethylene. High density polyethylene is the only pipe material type that can do this, as we temporarily change the OD of that pipe, make it small, then we pull it into place into the host pipeline and allow it to regain its shape. So this graphic shows you a slip lining job in New Orleans, where we're starting with a 30-inch cast iron pipe host. It's been tuberculated. It's been cleaned to allow and prepare that pipeline for receipt of the liner itself. The 32-inch HDPE pipe has been forcibly pushed through a reducer die. What you'll see on it there is an oil that they spray on the exterior of the pipeline to allow it to reduce the friction costs as it's going through the die. Then it's pulled into place at 20-inch OD and allowed to relax. Very, very stop process, very good way to do this. Similar in setup to slip lining and pipe bursting as we go through. Pipe bursting, if you're not otherwise familiar, we don't have a whole lot of time to talk about it now, but we will do a webinar on it a little later in the year. For pneumatic pipe bursting, high density polyethylene is the only pipe material type that can be used, and that's done for a lot of VCP, cast iron, and other things of that type. And static pipe bursting can use other material types. It's primarily set up for cutters or other things that may get through fittings and other things of that nature. When we're looking at trenchless technologies, we're looking at massive less excavation, which this lends itself to. Richard, did you have a comment?
Yeah, I do. I'm getting a lot of questions, guys, on resources, and I'm throwing references out there, and we may not have time to get to them. So please don't be afraid to look at the Plastics Pipe Institute, plasticspipe.org, because that's where all these calculators exist. And you'll be able to calculate a lot of the stuff that Alan's talking about here. Plus, don't forget about the new AWWA M55 manual, brand new this year. And I think it's really important this group needs to hear this, because all these questions I'm answering, I'm referencing. So I just wanted to stick that in there. Sorry, I'm out of here. I know you're tight for time.
Come on camera, everybody. We'll close off as we cruise through the resources here. If you have direct email needs, we are here for you. It's a nonprofit. We're here to help answer your questions and move your project along as we go through that. Peter, take it away.
Yeah, nice job today. Keep paging through the resources, Alan, just so people can look at them anyway. Doug Keller, great job on the material properties and the materials. I'm so impressed with you and the fact that you guys have created such a wonderful resin. Richard Kalasa, you and Doug answered 35 different questions today from the 250 people that were on this call. Dan Landy, your third production, good work, my man. And Alan Ambler, great job in this deck. You know, we're going to keep improving this deck to our audience over time. And please send dlandy@pepipe.org any requests or any help with projects that you want, and ask Dan for PDHs. That'll be part of his responsibility. Thank you all very much for staying to the bitter end. We've tried to keep it entertaining and interesting, but you guys have killed it because you asked so many great questions. So we'll see you next week on the AMA HDPE pipe. So long for today. Thank you very much to our panelists.
Thanks, guys.
Thank you.
Thanks, everyone.